can you hear me clearly?
I can hear you, yes. That's being
Okay. So thank you very much, Professor Rees, for joining us. So first of all, I want to say why we are trying to do this kind of interview. So first of all, we are still students, and we felt that we are coming from a developing country, so to popularize astronomy among the school students as well as the undergraduate students, we took that initiative that let's I mean somebody cannot directly represent the papers on archives, so someone needs to act as a mediator to tell the gist of the astronomy what is currently going in a direction. And also the school students will be very happy to interact with the astronomer or astrophysicist like you. So we took this initiative to ask the questions, and maybe Rifat can say something more about the open space project, then we will move on.
right.
Oh, okay. Actually, open space apparently seems we call it a magazine, but we actually don't believe that it's a magazine. It's a platform actually for the Bangladeshi students. That uh, I can share experience about of mine. That when I was in childhood, I didn't have enough resource to practice astronomy in Bangladesh, and especially in my mother language. So that's why we have decided to make a platform about where students of Bangladesh and also from India can practice astronomy in their mother language. So open space with a Urdu going forward, and as a part of this, we are talking to you.
I'm very glad to be able to participate.
Okay.
Thank you.
So let me introduce Professor Reach to the people who are watching, or maybe people who will watch later. So Professor Reach completed his PhD under the guidance of Professor Denis Sharma in 1967. After that, he worked as a research fellow at Caltech, Cambridge, and also IAS in Princeton. He is now Emeritus Professor of Cosmology and Astrophysics at Cambridge University, and where he was director of the Institute of Astronomy from the 1977 to 1982, and also 1977 to 1981. And he was also visiting professor in many institutes. I think most of the institutes in the world, like Harvard, Caltech, and Imperial College, and many more. So his research interest spans in a wide range of topics in astrophysics and cosmology, starting from the cosmic microwave background to galaxy, clusters, and quasars. He worked on the physics behind cosmic microwave background, which essentially confirms the existence of the Big Bang theory. And also the secondary anisotropies in CMB, was named on his name, which is Rees-Sama effect, which particularly I studied. He also made significant contribution in other topics like gamma ray burst, multiverse, and also anthropic reasoning. Now I want to say something that he was awarded many prizes for his outstanding contribution in astrophysics and cosmology, but it will take a long time to mention all of them. So I just want to mention a
Indeed.
few of like he won the Albert Einstein World Award for Science in 2003, Isaac Newton Medal in 2013, and Dirac Medal from ICTP in 2013, and many more awards. So once again, I want to thank Professor Reach for giving us his valuable time. Thank you very much. Now, I would like to introduce each other. So, I am Anirban Roy. I am working as a PhD student at CISA under Carlo Bacigalupi and Andrea Lappi, and I am working on the cosmic microwave background and large scale structure formation. Rifat, please introduce yourself.
I'm Ahmed Abdullah Rifat, studying undergrad with computer science and engineering at Jawaharlal University. I'm not from actually astronomy background, but I am really enthusiastic about this, and hopefully I will join in future in this subject as well.
Arnab, please introduce yourself.
Hello, I am Arnav Chakraborty. I am from India. I am currently pursuing my PhD from IIT Bombay. I am working on radio astronomy. Mainly, my work is focusing on upcoming radio telescope estimates.
Okay, So first part, as I said, I will ask some questions about the life of Professor Rees. So first question I would like to ask you that when you were a bachelor student, cosmology was a new field and considered as a fiction story. Which things attracted you to study cosmology in more advanced level and later to consider it as your career? It will be great if you start from your school days, that how you were attracted towards cosmology.
Yes. Well, I start my school days. I was quite good at maths and science. I was also very bad at languages, and therefore I concentrated on science and math at school and got into a university at Cambridge where I studied mathematics for my bachelor's degree. But I knew already I didn't really want to be a mathematician. I wanted to try and apply it to something. I thought I might be an economist or something. But by really chance, I ended up getting a place as a graduate student in the Applied Maths Department at Cambridge, and my first piece of luck was to be assigned to Dr. Dennis Sharma as my supervisor, who was a very inspirational person. And this was the mid-1960s, and I was also lucky because that was a good time, because as you say, before that time, cosmology was sort of a very speculative subject, theoretical, no observations, but we had in the mid-1960s the first high redshift objects, the quasars, and the first evidence for the Big Bang from the background radiation, the so-called afterglow of creation. And it was a good subject because one bit of advice I give to all you younger people is if you want to choose a subject to do research in, pick something where new things are happening. Because then the experience of the old guys doesn't count for much. You start on the same level as them. And I was lucky in being a researcher in cosmology when most of the topics were new.
Thank you very much. It is quite inspiring for us. Now,
Uh,
yeah,
so can I ask a question?
yeah, sure.
So, as a student, what was your reaction when you first heard the Big Bang theory? Because that time it was hard to believe when someone first got introduced, because there was something hype about materialism.
Well, of course, there was lots of debate about whether there was a Big Bang. That debate went back to before I was born, but the evidence didn't really become strong until in 1965, when Hengis and Wilson, two radio engineers, discovered this excess background radiation. They discovered that even empty space is not completely cold. It's warmed to 3 degrees above absolute zero by microwave radiation. And it was realized soon after that that this radiation was a relic of the hot, dense beginning of the universe. The universe was hot and dense. As it expanded, the radiation cooled and diluted and shifted into the microwave band, but it fills the universe, it's got nowhere else to go. And this was the direct evidence that our universe had once been very hot and dense. So that was really important, and soon after that there were other bits of evidence which supported this. And so the evidence for a Big Bang really didn't become strong until the mid or late 1960s.
Okay, great.
Oh, okay, so you, Professor, you did PhD under Professor Dennis Sharma, who is also the supervisor of Stephen Hawking, Roger Penrose, and many more scientists who are working now. So, could you please share your experience working with him or any good memories you would like to share with us?
Well, Dennis Sharma was a great enthusiast, and of course, good students learn from each other. So I learned from being in a group where there was good students he'd attracted. But he was very good at deciding what topics were important, what we should read, and what lectures we should go to. For instance, he got Stephen Hawking started by suggesting he should go to lectures by Roger Penrose at London University, and Roger Penrose's new mathematical ideas were really the impetus for all of the new work in relativity. which Hawking and others then did. So he was an enthusiast, and he had a feeling for what was important, and he encouraged us. And I think that was his main virtue.
Okay, thank you very much.
Good students learn from each other. That's great to see. Great to hear actually. Professor, from my curiosity, I am asking you a question. How many times have you met Professor Jamal Nusrat Islam? He is actually from Bangladesh, and I am very much interested about his life and his work life as well.
Sorry, whose work?
Professor Jamal Nusrat Islam from Bangladesh.
Oh, okay. Jamal Islam. Yes, well, he was a few years senior to me, and he had been supervised by Professor Fred Hoyle, who was the senior scientist at that time, and he had done some work with him in fundamental physics. But my main interaction with Professor Islam was that he wrote a paper and a book in early 1970s, I think, on the end of the universe, what would happen, the far future of the universe. And I also, at that time, wrote a paper about what would happen if the universe had a different end. He thought about the universe that would go on expanding forever and eventually cool down and become very cold and empty. I thought about a universe which would stop expanding and contract back to what some people call the Big Crunch, what happened then. So my common interest with Islam was the future of the universe. And of course I kept up with him until his sadly premature death.
Oh.
Hello?
Okay, yeah, Arnav?
Hello?
Yes?
Okay, I want to ask one question.
Yeah, sure. Go on.
Hello, Professor. Since you mentioned Professor Hoyle's name, so Fred Hoyle believes that in a steady state theory means there is no Big Bang, right? What do you believe?
So I didn't hear that last.
Okay, I can repeat Arnav's question. Yeah. So Arnav is saying, as you mentioned about Professor Hoyle, so Hoyle was the big supporter of the steady state theory. So, but your work basically confirms the Big Bang theory. So what do you feel about it? Because
Well, as you say, Fred Hoyle was the proponent of a different theory, the steady state theory, which was tenable until the early 1960s, then was disproved. Fred Hoyle never really got reconciled to the Big Bang theory, even in his old age. He believed in what I call the steady bang theory, a compromise theory. But of course, Fred Hoyle was, in fact, before I got to know him, probably the world's most creative astrophysicist. And between the mid-1940s and 1960s, he had more good ideas than anyone else on the subject. And his most famous work was on the origin of the periodic table. The wonderful idea that all the atoms in our bodies, that all the carbon, oxygen, and iron, were made inside a star, inside a big star, which derived its energy by nuclear fusion, by turning hydrogen into helium, helium into carbon, and oxygen, etc. And then, when that star died, it exploded as a supernova, threw out all this material into interstellar gas, and then new stars formed from that gas, including our solar system. So we contain in our bodies atoms of carbon and oxygen which originated in many, many stars all over the Milky Way, which lived and died more than 4.5 billion years ago before our solar system formed. So we are literally the ashes of long dead stars. If we're less romantic, we are the nuclear waste, the fuel that made the stars shine. And Fred Hoyle was the first person to really clearly have that wonderful idea. And that was his great achievement. He was a very man.
yes.
That's the interesting idea too.
Even though much of his science is out of date, I think his science fiction is very good. So I recommend some of his science fiction books too.
Yes. So thank you very much, Professor Rees. So in this section, we would like to ask two more questions because we are running out of time because we need to take other question by other people also. So, Rifa, do you want to ask something about what we discussed, and then we can go on?
No, you can go to the next question.
Okay. So I always think about it that some people say that cosmology is becoming like a religion, that what you believe and what you don't believe. You can believe on Big Bang theory, you can believe on multiverse or bouncing universe or whatever. So what do you think that what can be the challenge for us next century on working on the cosmology and on a perspective of a optimistic person? So, what do you think?
Yes. Well, I think it is not just speculation. I would say that now the evidence about the history of our universe back to the stage when it was only 1 microsecond old is as well established as anything that a geologist tells you about the history of the Earth. It's very well established, very good evidence for that. And that's an amazing achievement from the time when I started as a graduate student and we had no idea it was a Big Bang at all. We can actually tell with great precision what the universe was like at all stages from when it was a microsecond old up to the present. But of course, that progress brings into focus a new set of questions which we couldn't even have posed before. What happened in that first microsecond? What happened right at the very beginning? And there we don't know the answer yet. And the reason for that is that the physics then is so extreme, so hot, so dense, so energetic, that the laws that we can study in the laboratory are transcended. So we have speculations about that. So there are many questions, like what happened at the very beginning, why is the universe expanding the way it is, how much larger is physical reality than the volume of our universe we can see, and what will happen in the far future. All those are questions that we're now addressing. But I think many of the ideas about cosmology are now quite well established.
Okay, thank you,
We also
Professor. Yeah, we will hope for the best. And so, last question in this section, I would like. Yeah, do you want to say anything?
Nothing. I won't expand this session very much because we have some questions in our hand. So the last question from me, and for the students of Bangladesh and India, what will be the message to the students who want to study with astronomy, and what to make contribution in this field? How I would like to motivate them.
Yes. Well, of course, the advances in astronomy have taken place very fast in the recent decades, not because we are cleverer than our predecessors, we are not, but because we have had better instruments. And of course, the bigger telescopes that we have on the ground and in space have allowed us to make these observations. And in India, you have a satellite that's going around now. It's very important. You have the world's best low-frequency radio telescope, the GMRT, and you have access to other telescopes. So it's better telescopes on the ground and in space which have helped. And one other thing, and that is computer simulations, because we can't do experiments in astronomy. We can't crash stars together or galaxies together and see what happens. But we can, in the virtual world of our computer, just that. We can ask what would happen if two galaxies crash together, and we can simulate it, and you may have seen movies of the results of these simulations, and we can compare those with what we actually see in the sky, and therefore test our theories. So it's the new equipment, both telescopes, spacecraft, and computers, which have allowed us to make this progress. And I would advise young people to become expert in computing, because computing is going to be crucial. And I feel a bit of a dinosaur because I'm not such an expert in computing as many of my younger colleagues.
Okay. Okay. Thank you very much.
Then I think I have an advantage since I am from computer science background, and if I move to astronomy, that may help me.
Right. Yes.
Okay. So we are moving to the next section. So first question is asked by Samira Tasnim, simulated.emission@gmail.com. because I want to mention also email to make them unique. So here she actually asked three questions. So first question is, do we need a new constant to figure out what happened before the Planck time?
We certainly need a lot of physics we don't yet understand, because we know that if we extrapolate back to the very early universe, we need to have a theory which combines gravitational theory with quantum theory. And as you know, we still don't have such a theory. And until we do, we won't be able to answer that question. So this is a big challenge for 21st century physics to put on the two great achievements of 20th century physics, which were Einstein's relativity and the quantum theory, to have a unified theory which can apply when the entire observable universe was squeezed to a microscopic size, so that quantum fluctuations could, as it were, shake the entire universe. So we need a new theory. Until we have that, then many mysteries will remain.
And she asked also, how close are we from the unification of the four fundamental forces of the nature?
I think we're quite a long way. There are lots of ideas being pursued, and the most intensively pursued idea is string theory.
String theory, right.
Been
Yeah.
pursued for 25 years or more, and it involves fascinating mathematics, but it's still not clear whether it's right. The reason is that it's very hard to get a link between this very elaborate theory and anything we can actually measure or observe. So we don't know, but it's the most intensively studied theory. One thing it does tell us, I think, is that any theory that applies to the very early universe may violate some of our intuitions. We're familiar with the idea that in the micro world of the quantum, things behave in a way that's not in accord with our intuitions. But when we go back to the very early universe, we may have to jettison other intuitions, like the idea that space has three dimensions and time just ticks away. Space and time may be intertwined, or there may be extra dimensions beyond the three dimensions of space and time we're used to. So we have to expect something which is far from our intuitions and very hard for us to understand. And I do often wonder whether some of these theories may be beyond our capacity to understand. It could be that there is a theory that even the cleverest of us will never understand it. But let's hope that's true, and let's hope people believe it's not true. Unless they think it's possible, they won't be motivated.
Yes, absolutely. And our last question is, can we recreate the process after Big Bang, ever so slightly to unify the forces? So maybe she's trying to talk about LHC or something. So
Yes, yes. Well, it's true that many of the unified theories may have consequences at low energies that we can observe. It says about something called supersymmetry, and so they may be something we can observe. And of course, the LHC, which revealed the Higgs particle, has sadly not revealed any other particles. But we want to know about other particles because of their relation to a unified theory. And also, of course, something we haven't mentioned yet is that the universe contains not just ordinary atoms, but dark matter. It contains about 5 times as much stuff in the form of some kind of particles, which we know are collisionless. They move around like a swarm, and they don't have any electric charge, and we don't know what they are. Some people hope that the LHC would have produced particles which would have been candidates for the dark matter. It hasn't yet. But we want to find what the dark matter is, either by LHC experiments, by direct measurement underground of detecting it, or perhaps by looking in space and seeing if the particles of dark matter sometimes annihilate each other to produce a gamma ray or a positron, or something like that we can detect. But so far, we don't know at all what the dark matter is. And if we did, it would solve a big problem. Of course, it's an important feature of the universe, but it would also give us new clues to physics beyond the so-called standard model.
okay, thank you. So Rifat, you can go on.
Okay, I am asking the next question. It's someone named Tashfiq Rahman. So So he asked two questions. The first one is, if you had to explain the relation between space and time, I think it's far from our topic today, but it's an interesting question. But if you had to explain the relation between space and time to a school going like 9 to 11 years old of guy, so how will you describe it?
Well, with difficulty is the answer. But I think you can you can draw a little diagram, can't you, quite easily, where you plot time against one dimension of space. You can plot the position of a car or train in that sort of way, and you can also plot the tracks of other objects, and then you can draw a sort of map and show how things move in time as well as in space. And of course, we're familiar with pictures like that. But of course, the one big difference is that in the spatial dimensions, the three spatial dimensions, which is forward and backwards, up and down, left and right, you can go either way. Whereas in the case of space, can only go one way. We can't freely decide whether we go forwards or backwards in time. So time is a different dimension. It's a dimension we are trapped in a way we are not trapped in a particular position in space. And that is really still a very deep mystery.
Okay, so the next question from Tashvik is, we all know that the velocity of expansion is increasing from time to time. So what will happen if it reaches at the velocity of light? Interesting question.
Well, the universe is expanding, actually getting further away, but also been realized in the last 15 or 20 years that the expansion is speeding up. And that therefore means that if you watch a galaxy, it's getting further away. It's moving faster and faster. So the redshift, the Doppler effect of its light, is getting bigger and bigger. And so if we were still alive in a few billion years, then the galaxy we are to now would have almost disappeared. And it would be moving away at the speed of light. And it's rather like what happens if something falls into a black hole. If you fall into a black hole, then of course it's bad news for you because you fall into the center and you get squashed or torn apart. But if I'm watching at a distance and I send a student into the black hole and I watch the student falling in, then of course it's bad news for the student. But what I see from outside is that as the student falls in, they get to a surface, which is a surface where, in effect, the escape velocity is the speed of light. And what happens as they get near that surface is that because the Doppler shift gets bigger and bigger, their clock seems to run slower and slower. So however long I watch for, I never see them get beyond that state. That's what happens if you watch something falling into a black hole. And similarly, in the accelerated universe, if we watch a galaxy, we will never see the distant future of that galaxy because we will see its redshift getting larger and larger, and clocks on it would run slower and slower compared to ours, but we will never see far future. So there's a limit to the amount of space and time that we can, even in principle, observe.
Okay, thank you. I think it's very interesting questions, and also the answer is very, very promising.
Very interesting, right?
Okay, so another question is from Arafat Rahman, Sahajan, I think Sahajan Sarkar 48954 @gmail.com. So he said the universe is expanding, but we know it needs space to expand anything. What is that space? Does it really exist?
Well, space exists. We are in it, and even a vacuum has some existence because we know now it has some energy in it, which is the energy that pushes the accelerating universe. We know that a gravitational wave going through space can make it shake, so it's like elastic. So we know space is a genuine substance which has properties. But the other point about space is that it has no edge, and if when the universe expands, you can think of the amount of space expanding with it. So it's not as though there's the space and then something beyond it. There's just space which goes on and has no boundary.
So we can say that space remains in itself, right?
Yes, that's right.
Okay.
So
Okay.
I think next two question is similar, so we can ask him together. I think Muhammad Islam and Mehdi Hassan Mehdi. Rifat, you can go on.
We all know the universe is expanding. Is there any possibility that the universe will start shrinking? And if there is possibility, then what will be the ultimate fate of the universe?
Very good question. Well, long-range forecasts are never reliable, so we don't know. But of course, the simplest long-range forecast, based on what we know, is that the universe will go on expanding. The galaxies will accelerate away from us, and eventually, if you were in the universe in 100 billion years, you would find it rather dull, because apart from our own galaxy and its immediate neighbours like Andromeda, everything else would have disappeared. It would be a very empty universe, and a very cold universe. But that assumes that the laws go on as before. We don't understand this force that is making the universe accelerate, the force latent in empty space. It could be that that force will go away, even reverse. And if that happens, then the future of the universe will be quite different. It could then stop expanding and then recollapse. So the galaxies start falling towards each other. They display blue shifts, not red shifts, and eventually everything will crash together in a very hot debris, rather like the Big Bang that set the universe expanding. So this would be the big crunch.
Okay.
And this would be a possibility, but I think no one expects this to happen in less than 20 billion years. So, sorry, that
So,
could happen 20 billion.
Another question arises.
But just I want to interrupt. We did a technical mistake because we didn't say the name of the questioner. So it was Muhammad Islam, mislam310@gmail.com. Thank you for your question. Yeah.
Oh, thank you, Mr. Ivan, for remembering me.
Yeah. Sure. Go on.
But then, this another question arises, which also arises arose in my mind, and also in the next question that what is you said the ultimate fate of the universe, but my question is, if the universe crashes together, then where will be the objects of energy that we have now? So, can there be any chance of recreating another universe, or nothing? It will vanish into nothing.
Well, I think we can't answer that question really for the same reason we can't understand the very early Big Bang, because the conditions would get so extreme that the physics we understand isn't sufficient. So we would need to have something like string theory, unified theory, to understand what would happen. Space and time will get mixed up in a very elaborate way. We don't know what would happen. But that raises another issue, which is that some people think that even if our Big Bang leads to an ever-expanding universe, maybe there are other Big Bangs. Maybe our Big Bang was the only one. And this is another interesting idea. And there are theories called eternal inflation where that happens. So these are speculative, and they're all speculative because we have no direct observations and we don't have a relevant theory that applies to the early Big Bang. But these are certainly options which are credible in the context of our present ignorance.
Okay.
So,
yeah, go on.
Go to the next question from Hasmat Ali.
Yeah. So next question is from Hasmat Ali at ha63@gmail.com. So if any object enters the black hole, where is it lost? Does it keep orbiting into black hole or it is pounded?
Well, if an object falls into a black hole, then it is lost from view by us, and according to theorems which were first proved by Roger Penrose in the 1960s, it will get to so-called singularity, where everything goes infinite, and that really means we need to new physics. So it will get destroyed. There is a very fundamental question, which was first raised by Stephen Hawking more than 40 years ago, which is whether the information is completely lost of what goes into a black hole, or whether, in some sense, there must be some memory of the way in which a black hole grew in mass and what went into it. There is still a debate 40 years later about whether there's information lost in a black hole, or whether somehow the information is stored just outside the horizon of the black hole. We don't know. But if you were to fall into a black hole, then the gravitational forces, the tidal force, that's a force between your head and your feet, that gets bigger and bigger as you fall in, and you get torn apart, and only some new physics can save you.
Okay. Thank you. The next question is from Tahim Sakib. His email ID is nebulastar333@gmail.com. Very interesting email, I think. His question is, once Albert Einstein said that there is no existence of anything called cold. We only feel it because of the difference of temperature. Is there any place in our universe where there is nothing called heat or temperature?
Very interesting question. It certainly seems that the microwave radiation left from the Big Bang that fills everywhere in space, and so in the natural universe, there's nowhere that would be colder than 3